All right, ladies and gentlemen, let's keep going here. We're not going to be in the decimals activity for a minute or two. We're going to just get some notes done. Now, we've been talking about piecewise defined functions. Believe it or not, the absolute value function is a piecewise defined function. And we're going to just talk about that piecewise defined function a bit right now. And I just want to talk about the absolute value graph. It's something that students don't understand necessarily very well at this development of their mathematics, and that's okay. You know, we're this part of this class is to take you to a higher level, so you're better prepared to handle, everything that follows. And so, that's going to be a theme that happens a lot. Welcome back, everyone. We're going to be revisiting things that you've seen before and hopefully kicking it up a notch or 10, depending on where your understanding was. And so if you think about the graph of the absolute value function, as we talked about it the other day on Monday when we went through the graph, a bunch of parent graphs, it was just, a V essentially. It was two linear pieces that looked like this and like this. Okay. Well, if you think about what we were just doing in graphing piecewise defined functions, you should be able to think now and look at this graph and say, hey, that's a weird looking graph compared to how most graphs look. We should be able to write a piecewise defined function for this. And we're going to do that together. Don't panic. Usually the initial understanding that students get with the absolute value function is that it's the distance from zero. That's one concept, and it's not wrong. Okay, don't let me mislead you. But a lot of students, their understanding of the absolute value function is its distance from zero, which is okay as a beginning understanding. And then there's other interpretations as there's one that's worse, where students think, well, it's not negative. Well, that's true, but that's not a very good way of understanding it. And I want you to think about it at a higher level than that. Let me give you the piecewise definition here. I'm still letting people in the room, by the way, so that's why I keep kind of getting distracted. If we were to look at this graph and start to just write a function for each of these, this right-handed piece over here, it's just a line with a slope of 1, it's going up 1 over 1, and hitting the origin. So this is just y equals x, that piece. But keeping in mind that we can't put in, this piece doesn't continue into the third quadrant. It's only for values of x that are greater than or equal to 0. But what about this piece on this side over here? This piece over here, well, this is just a line. It's got a slope of -1. It also hits the origin, so it's negative x. But it doesn't keep going over here into the fourth quadrant. It's only when x is less than 0. Now, I did something there. Notice I did not include the or equal to sign here, but I did over here. I'm doing that with the intention of knowing where I'm going with this. If you look at each piece independently, you could include 0 on both independently. But when we put them together, we wouldn't want to include 0 on both. As I said earlier, we don't want the definitions in our piecewise defined functions to overlap. So I'm not going to allow this to overlap. So if I just recognize that, then I have my definition of my piecewise definition of the absolute value function. The absolute value function is just x, as this piece is telling me over here, when x is greater than or equal to 0. And as this piece tells me, it's negative x, or as I like to say, the opposite of x when x is less than 0. This is your piecewise defined definition of the absolute value function. And I think you should memorize it, because I am going to ask you to remember it and use it quite a bit, especially when we get into calculus. And so the sooner you commit it to memory, the better. Now, although you can see the graph, and I just justified where these pieces come from, a lot of students still have trouble with one of the pieces. Specifically, the trouble they have is with this piece right here. And this is because they have that poor understanding of, well, it's absolute value of x, and it's never negative. And although that's true, the output of the absolute value function is never negative. This doesn't say the output is negative, and this is where the misunderstanding happens. A lot of students think that when they see a negative sign, that means the quantity they're talking about is negative. That's not true. I can give you counterexamples to that all day long, okay? -0, that's not a negative number because 0 is not negative nor positive, and 0 times a negative number just becomes 0. It's not negative. Just because you see a negative doesn't make the quantity negative. What if I had the negative of -4? That's not negative, that's positive, okay? Just because I see a negative doesn't mean the quantity is negative. The misunderstanding that we have is that you see a negative and you think it's got to be negative. No, it depends on what the negative is being applied to, okay? Look at this side over here. This side over here tells you already that x itself is negative. And if x is already negative, then taking the opposite of x means you're talking about a positive number. And that's the way you have to think about this. Let's apply this definition really quickly in to a particular example. So let's say we're taking the absolute value of 3. Now, you know the answer to this question. It's not the point for me to teach you the answer to this question. You know the answer to this question. My point here is to teach you how to use this definition so you get the answer that you understand. Okay, so I'm going to go through the thought process here so you can start to adopt this thought process when you have to deal with the absolute value function, especially in its piecewise form. So what is this definition telling me? Well, I have to first think in terms of two different pieces here. I got the piece where x is greater than or equal to 0, and I got the piece where x is less than 0. So the first thing I need to do is identify whether the input is in the first interval, whether the input is greater than or equal to 0, or it's in the second interval, whether I got to determine if x is less than 0. That's the first thing I have to determine. Now, this piece, obviously, 3 is greater than or equal to 0, so 3 is in the first piece, okay? So that's the first thing I identify. 3 is greater than or equal to 0, therefore, I'm talking about the first part of the definition. Now, let's focus in a little bit on the definition a little more closely. What does the definition say? And I want to interpret it in a way that, again, is hopefully more functional in how you think about it. Notice that the input is x on this side over here. What's the output if x is greater than or equal to 0? It's exactly the same thing. It's also x. So what this definition is telling me that is if the input is greater than or equal to 0, the output is exactly the same as the input. And that's a good way of thinking about this. When the input is greater than or equal to 0, when the input is non-negative, then the output is exactly the same as the input. And since my input is greater than or equal to 0, the output here is going to be exactly the same thing. Now, what happens if we plug in a negative number? Again, let's model the thought process. I'm going to go look at the definition. I'm going to identify which interval it is in. -3 is less than 0. It's in this second interval over here. Now, what does the definition tell me? The definition here tells me that if my input is x, my output is the opposite of x. Notice how I keep using the word opposite here because it's a better way of thinking about it than thinking -x. For two reasons. One, -x confuses a lot of people. And two, the opposite gives a better and truer characteristic of what's happening here, okay? If my input is x, my input is -3, my output is the opposite of the input. And the opposite of -3 is +3, like you already knew, but that's how this definition works. And that's a better way of understanding the absolute value function as opposed to distance from 0, or even worse, it's just some non-negative number. Questions, comments, or concerns up to this point? this definition will come back to haunt you at some point. All right, then we're going to move on to the next idea. We've done that. We've done that. Okay. Now, mathematicians are lazy people, ladies and gentlemen. If you have this high and mighty notion of what a mathematician is, you just got to think lazy, okay? And so they always find ways of shortcutting things so that they don't have to work too hard. Now, that might sound pretty good to a lot of you. Sounds good to me. Of course, I studied math, so it's right up my alley here, so to speak. So if we had a lot of terms to write down that we wanted to add together, say we were going to add together 5 to the 4th power plus 5.3 to the 4th power plus 5.6 to the 4th power, I'm already getting bored with this. And this was to continue on for God knows how many terms. Let's say that this went all the way out to like 56 to the 4th power. Notice already that as a mathematician, I'm getting lazy. I don't even want to write all the terms down. I just put a plus ... to say, oh, the pattern's going to continue. And then eventually we're going to end at 56 raised to the 4th power. Are we okay with that so far? How lazy we are? Anyways, don't answer that question. Mathematicians have a special notation for this called sigma notation. A special way of writing this out so that it doesn't have to look like this. You don't have to show so many terms. It's more compact. It's easier to write, harder to understand for some. It's also called summation notation. So there's 2 different names for it. So if you see either of those phrases, they mean the same thing. And the sigma part comes from the fact that we use the Greek letter sigma, the capital Greek letter sigma, which kind of looks like an E, but it's not. It's the capital Greek letter sigma. And in mathematics, when you see a sigma, it represents a sum, meaning we're going to add a bunch of things together. If you've never seen this before, well, there's your introduction. If you have seen it before, then I'm probably talking too slowly for you. But the nice thing about this, I'll come back to what I did up here in just a moment. So give me a minute. I'll come back to this, okay? So, because I want to be able to write what I just circled in red into summation notation or sigma notation. But for a moment here, let me just explain a couple things. Let's say we have, well, let me show you what the structure looks like. So the structure could look something like this. This is an example of some sigma notation or summation notation. Now, what do all these things mean over here, or what are they called? These 2 pieces right here are called the indices. That's plural. Each are called an index. Okay, that's an index, and this is an index. Okay, the letter down here is the letter that's in the expression over here. This is called the argument. So whatever letter here you see is going to be the letter in here. Now we start our indexing values at 1 or some number. Actually, it doesn't matter where we start it. We can start it at any number. It just has to be an integer. And then we're going to end it up here at some other number, which is also going to be some integer. Do you guys know what the integers are? I sometimes use words and I forget the students don't always know what those words mean. If you don't remember what the integers are, I'll tell you. You might want to make a note of this. The integers are essentially the counting numbers, their opposite, so the negative of them, and 0. Let me say that again. The counting numbers, their opposite, and 0. 1, 2, 3, 4, 5, and so forth. -1, -2, -3, -4, -5, and so forth, and 0. Those are the integers, okay? 1.5 is not an integer. Pi is not an integer, okay? Integers are the positive whole numbers, the negative whole numbers, and zero, or sometimes we call those the counting numbers, the opposite of the counting numbers, and zero. So the index values always have to be integers, ladies and gentlemen. Always, always, always. Have I said enough always there? I don't know. Because some of you, some students I've had in the past, of course, none of you are like this, but some students I've had in the past don't seem to get that message. Even if I say it 3 times or 5 times or 8 times, it doesn't matter. They don't always seem to get it, which becomes a problem because then I'll get answers on quizzes or tests that have decimals in the index, which is automatically wrong because you cannot have decimals in the index. I should say non-integer decimals in the index. You have to have integers. Anyways, I'll get off my high horse there. What does this mean? This means we're going to sigma summation, and we're going to add together a bunch of terms. What are we actually adding together? We're going to plug in 1 for I. And we're going to get, and I'm not going to simplify this. I want you to see it written out, at least for a couple terms. So my first term is whatever I get when I plug in wherever I starts. In this case, I is starting at 1. It doesn't have to start at 1. It could start at 2. It could start at 0. It could start at any integer. So I put whatever I starts with. That's the first thing I put in for I. That's the first term. Then I'm going to add to it. And I'm just going to go down the integers now from 1 to 10. So I'm going to plug in 2. So I'll get 3 times 2 plus 4 squared. And then 3 times 3 plus 4 squared. And then we're going to continue. Where do we stop? We stop when we get to 10. And I'm already getting too lazy to write it out. So I would get up to 9. That's the second to last term. And then I would go 1 more. I'm just showing you the second to last term. I don't know why, just because just trying to show you for a moment. It looks like this. That's what this means. Now, what is it as a sum? What is it total? I don't know, and I really don't care at the moment. The point of this discussion is not to know the sum, the value that this actually totals. The point of this is to understand the notation, to be able to expand it, write it out if asked to do so. And I will ask you in some future assessments to expand this sigma notation or expand this summation notation. And I'll write in the instructions, do not find the sum or something like that. Because I don't want to know that you can total it up or type it into the calculator and total up. I want to know that you understand it, and I want to see that you can write it out if asked to do so. Now, what if we already had something that was written out like up here and we wanted to write it in sigma notation or summation notation? Well, let's go figure out how we can do that. Actually, you know what? I'm going to pause for a moment. In my brain, I'm thinking maybe we need to do one more example of expanding first. Oh, I got some practice expanding in the Desmos activity. All right. I'm going to call an audible here, ladies and gentlemen. I'm going to send you all to screen number 19. It's a little out of order. On screen number 19, I want you to expand, do not find the sum, the sigma notation that's given on that screen. You can do like I did here. You can put your plus ... dots. Give me at least a couple terms at the start and a couple terms at the end or something like that. I definitely don't want you to write out all 18 terms for this one. And by the way, there are 18 terms, not 17, because if you subtract 5 from 22, I know you get 17, but that means you're not counting the first term, which is incorrect. There are 18 terms in this one. Juan, after your dots, make sure you put a plus before that that parenthesis after the dots. Notice, ladies and gentlemen, I have a plus right over here, okay? There's a plus after you put the 3 dots, put 3 dots. Our ellipses tend to be 3 dots, and then a plus, and then continue the pattern. You guys got to stop exiting out of these things. In case you exited out of the activity, here it is. Here's the link. Alessandro, why did you put 1 in first? There you go. You read my mind because you started doing that before I said anything. Isabel, why are you starting with n equals 1? Sophia, I don't want the numbers. I want the expanded form, just like I wrote on my screen. Notice I know I can do 3 times 1 is 3, plus 4 is 7, 7 squared is 49. I don't care about that at the moment. Well, I want to see that you can show me the mechanics of how the notation works, not do the calculation. I'm going to open up screen 20. It's the same thing, just a different expression, different indexing values. Alessandra, don't keep going. Don't give me every term. Put a plus dot dot in there and jump to the last term, please. Elias, you're missing a plus between your last 2 terms. Crystal, you didn't, after your first term, you didn't put the 5th power on any of the expressions on 19. Samuel, on a quiz or a test, I'm going to expect more than the first and the last term. I'm going to need at least a couple at the beginning. Usually 3 at the beginning and 1 at the end are fine. If you want to do 2 and 2, that's fine. But I'm going to be expecting about 4 terms if you want full credit. So there's a weird occurrence in mathematics. I guess this occurs in other subjects as well, although maybe the transparency of it may be a little different. You realize you don't have to be right in mathematics to get credit on a quiz or a test. You just have to convince me that you're right, whether or not you actually are right. Now, it's hard to fool me into thinking you're right when you're not. But let's not fool ourselves. Don't just automatically assume you're right. Make sure of it. Math is a logic game and we've cracked the code. We'll find out if you crack the code. I got to grade the quizzes still. Logic is definitely a foundational aspect of mathematics, although we don't always rely on it. Because we're human, we're flawed, we have bias and opinion, we err, we start to believe things that aren't true. What just happened? Okay, nothing good. I'm on screen 20, kind of checking things out. So when I give you advice on things, I'm trying to teach you how to be right, how to convince me that you're right, or somebody else that you may have to deal with. Alexis, before your last term, after the 3 dots, make sure you put a plus. There you go. So this is easy. I mean, once you understand the notation, there's nothing challenging about expanding these things. I don't know why I put these slides in this order. For some strange reason, I put the expanding after the more complicated rewriting the sum into summation notation. That's all right. All right, ladies and gentlemen, I'm going to revert back to that original sum that I had written down. And I want to write this sum in sigma notation. So I'm going to copy it down over here. 5 to the 4th plus 5.3 to the 4th plus 5.6 to the 4th plus ... plus 56 to the 4th. All right, just making sure I got it right. Now, generally speaking, these things are not too complicated to write in summation notation at this level for the examples that you're going to see in this class. Yes, they could get much more complicated in higher level math classes, but for the things that we're going to be dealing with in this class, they won't be too complicated. Okay, they're all pretty much going to follow a similar pattern to what I'm going to describe to you, although not perfectly, but for the most part. What you want to look for is similar structure throughout the entire expression. What do each of these terms have in common? Well, they each have a 4th power in them. So when I start to build my summation notation here, I know my argument is going to be something raised to the 4th power because every single term has that 4th power in it. If you look at the examples where you were doing the expansion, the constants, the thing that was in every single term was already there in the summation notation, okay? Just going back up here, we had a square, everything was being squared. We had the 3, everything had a 3 as a factor of that first term in the expression. And then we were adding 4, after we did the product with I, and that was there every single time. So we're always looking for those things that are in every single term, and we can automatically populate our summation notation with those things, okay? Now, in the Desmos activity, their default indexing variable is n. Doesn't have to be n. I is very common. J is very common. K is very common. X, Y, Z, those are not common. We typically do not use X, Y, or Z. There's no good reason for it. So it's not wrong to use those letters. It's just not typical. So I'm going to use I in this case, but in the Desmos activity, it's going to automatically give you an N. Oh, by the way, to get the summation symbol, when you're in the Desmos activity, you type in very simply sum, S-U-M, and it'll give you the summation sigma for for writing a summation expression or sigma expression, and then it'll start you with n. So you just use n in your expression. I'm just going to use I just so you see something different at the moment. Okay. Now, at some point, I'm going to have to figure out where I'm going to start I, and there are many choices depending on how I write my expression here. I'm also going to have to figure out where I'm going to end it. Again, that depends on what I put in here, and I'll show you different versions for this particular example, okay? What's changing? Well, what's changing, we go from 5 to 5.3 to 5.6, and that pattern's got to continue. That's what this is telling us right here. Just continue the pattern, adding 0.3, so 5.9, and then 6.2, 6.5, 6.8, and so forth, all the way until we get to 56. Now, I'll be honest with you, ladies and gentlemen, I hope 56 works properly because I didn't do a calculation to figure it out. I'm taking a guess. And if I guessed wrong, then they'll have a mistake on the screen. And that's okay, because the mistake will tell us something. And part of me wants to be wrong here so I can show you an issue that comes up. But I'll show you the issue anyways, even if I happen to be right that 56 does work. I'll explain everything I'm referring to in just a moment. So because we're growing, the base is growing linear here, and most of the examples that you're going to be dealing with will have an expression that is growing linearly. All we have to do is write an expression for a line and put that inside our parentheses here. What do I mean by that? Well, what's our first term here? 5. That's the first term. And then what am I doing to get the next term every single time? I'm adding 0.3. So I just got to figure out what I'm adding every time, add that. But I want not just that, I want multiples of that. So 0.3i. If you're confused, good. Maybe I can teach you a little something. Let's check this out for a moment. If I put I here and 5 plus 0.3i over here in this column, we can calculate some values. For instance, if I is equal to 0, we get 5. If I is equal to 1, we get 5.3. If I is equal to 2, we get 5.6. This seems to be working. It looks like I got to start my index at 0 because that's what produces the 5 that I have in my first term. The question is, where do I stop it? Well, I have to figure out the value of I that produces the 56 over here. Where does the 56 come from? For what value of I do we get 56? Well, I could just write an equation for that, set 5 plus 0.3i equal to 56, and solve. Now, here's the issue you want to watch out for. This is where I'm kind of hoping I made a mistake, even though I don't think I did. If I solve for I correctly and I don't get an integer, you guys remember I harped on the fact that the indexing values have to be integers. If my answer comes out to be a decimal that's not an integer, then my 56 is wrong and I made a mistake. Mr. Francis made a mistake in that number that he put there because I just seemed like it will work. I wasn't sure. But if it does work out to be an integer, then I did guess right. Okay, so let's subtract 5. 0.3i is going to be equal to 51. And then I have to divide 51 by 0.3. And I'm not going to use a calculator. I'm just going to shift decimals around. That's 510 divided by 3. And I don't know if you know, but 51 is divisible by 3. It goes in there 17 times, so it's 170. Just double checking my arithmetic here. Yeah, it looks like if you've got a different number because you used a calculator, then maybe you're right and I'm wrong, and you should tell me that you're right and I'm wrong, and I would be perfectly fine with that. So my top indexing value is going to be 170 because that's the value of I that produces 56. And what I'm going to put in here is that 5 plus 0.3 I. And that's going to produce the terms of this summation, of this sum, I should say. All right, let me put you back on a different screen. Pacing. Somebody ask me something?
Yes. Can you repeat again how you got the how I equal the zero term, please?
Oh, I forgot. I was going to do this another way. I want to point out something for a moment. I opened up the screen. If you want to pay attention to that and work on that, that's fine. But I am going to show you how to write this in different forms. How did I know that we're going to start at 0? Because that's the way I created it. I know that's not a very good response. It's not a very good answer. But notice that my first term is 5. And then I wrote my expression as 5 plus the delta, the amount it's changing each time. So I'm adding 0.3. So I went 5 plus 0.3 times I. So that means I need the 5 to be the first term, which means I need this whole term 0.3 times I to disappear when I plug in my first value of I. How does it disappear when I plug in my first value of I? I has to be 0. I don't know if that was very helpful.
Oh, that helped. Thank you.
Okay. You're welcome. All right, let me show you another thing, okay? Maybe I don't want to start at 5. Maybe I wanted to start at a different value. And maybe I'm thinking, well, if I continue this pattern back 1 for just a moment and I subtracted 0.3 from 5, I would be at 4.7. Maybe I want to start there. And then I add 0.3 I because that's why I'm getting each new term. If I did it this way, then the first value of I that I would plug in to produce 5 would have to be 1 because 4.7 plus 0.3 would be 5. And that's obtained when I equals 1. When I equals 2, then I would put 0.3 times 2, which is 0.6 plus 4.7, which is 5.3. So another version of this, which is correct and equivalent to, but a little bit different, I'll put the top number up in just a moment, is going to be 4.7 plus 0.3 I. Now, I'm not going to stop at 170 again because that worked for this one here. I've shifted this down by 1, so that means I'm going to have to put 171 in here. And if you don't believe me, you could just set this equal to 56 and solve, and you'll find out that you get 171 after you subtract the 4.7 and divide by 0.3. You'll get 171 instead of 170. So you can find it the same way. You can set it up however you want to set it up. We could do it again. We can do this an infinite number of ways. Maybe I don't want those. Maybe I want to start at -1 instead. So if I had 5.3 plus 0.3 times I, now here, I'm going to need I to be -1 to start, because when I is -1, then I'm going to get 5.3 plus -0.3, which is 5. When I plug in 0, then I'm going to get 5.3. When I plug in 1, I'll get 5.6. So I could write it as a sum from I equals -1 from I equals -1 to 5.3 plus 0.3 I raised to the 4th power. Now, where am I going to stop it? Well, I got to go 1. I got to stop 1 earlier. I shifted everything to the left 1, so I'd stop it at 169 instead of at 170. So I just give you 3 different ways of writing it. Now, I'm not asking for you to be able to write it in multiple ways, but it's not that hard. They're just shifts of each other. Notice that there's always a 0.3i in all of these because that's how much each term is growing by. So that's always going to be there. The fourth power is always going to be there. It's just we chose a different starting point. Whether we started with the first number 5 and let I equal 0, we start with what would be the number before before 5 if we let I equal 1. Or if we start with the number after 5 and let I equal -1. And we could do this literally start at any integer that we want and just shift it accordingly. And we could still be correct. All right, you should be on screen 16 trying to write in summation notation. Result there. I'm missing people right now. Where are you? If you're not in the Desmos activity, come on, let's go. If you think you're going to be able to learn this stuff later, some of the point by not paying attention now and somehow by osmosis get it, you're not. Just doesn't work. We go way too fast. So those of you who are disengaged because you're doing some other nonsense right now, remember why you're here. You're trying to accelerate in mathematics. You're trying to get to a higher level. Sacrificing the other things that you would prefer to be doing right now than listen to me drone on and on like an old man. Well, too bad. You got to listen to me if you want to get better. Remember, type in SUM to put the summation symbol onto your into your input. SUM, just the word sum. I'm going to open up screen 17. Remember to type SUM. Now, those of you using I in your argument, you got to change your indexing variable, the letter below sigma to I also, if you want to do that, or use the one that they give you, use N. Isn't it? Monique, if you start on, this is screen 16, if you start on n equals 1, you're going to have your first term be 2 cubed, not 1.5 cubed. Isabel, on screen 16, you forgot the exponent. Angel, if you plug in 1 into your expression, you're going to start with 2.5 cubed, not 1.5 cubed. Valeria, you have I in your expression instead of N, or you have N in your index instead of I. You need what, those need to match. Ariana, you have your first term would be 2.5 cubed, not 1.5 cubed. Samuel, you used X, and there are no X's in the rest of the problem. Josh, don't, I said type in sum, not sigma, S-U-M. You chose the harder word to type in. Don't type in sigma, type in sum, and you'll get a summation, sigma. There you go. Whoa, Sophia, your upper index is way too large. Stephen, remember I said no decimals in your index, integers only. N cannot be 1.5. Don't do that. Juliana, you seem to be doing fine at the start. Where's your cube, by the way? Other than that, you got it. Yeah, you got it. So I don't know what you seems like you do know what you're doing. If you have a more specific question, you can ask. If something's still confusing, that's normal. I'm not moving off of screen 16 yet, ladies and gentlemen, because a lot of us don't have it, aren't done, or have mistakes. Now, Stephen, your upper index, the 20 is wrong, but everything else is looking a lot better. Josh, the 40 is wrong. If you put 40 times 0.5, that's 20. 20 plus 1.5 is 21.5, and the last term is 20. So you got to fix that upper limit. Ariana, your first term is still wrong. If you plug in 1 for n, you're going to start at 3, and we need the sum to start at 1.5. All right, most of you have it, but for those who don't, and that's okay, we're still learning here. Let me go write this out somewhere. My zoom factor is not good right now, so let me adjust that too. So this is screen 16, I think. All right. Yeah, 16, 1.5 cubed plus 2 cubed plus 2.5 cubed all the way out to 20 cubed. I'm sorry, I just realized there was one other little thing I wanted to get prepared to show you for the next topic that I did not do yet. Anyway, don't worry about that. So what's always here? Well, something being cubed. So we're going to have a cubic or cubed term right here. What's changing? Now, I always like to just start with the first term, the 1.5. That's just how my brain likes to do it. You don't have to. If a different teacher taught you to start it someplace else, that's fine. I showed you in the last example 3 different ways of doing this. I'm not concerned that you always start it the same place I do. I want you to have correct mathematics and correct justification for it. So I always start with that one, and then I add to it the delta, what we're changing by. We're growing by 0.5 times our indexing value. I'll switch to n because that's what you guys are typing into the system, most of you at least. And so if I do this, then n is going to start at 0 because 0.5 times 0 gives me my first term of 1.5. And then this is what I'm going to put in here, 1.5 plus 0.5 times n, quantity cubed. And now I just got to figure out where to stop it. So I set it equal to the last term that's growing in as part of this linear pattern. And then I just got to do the arithmetic here, the basic algebra. So if I subtract 1.5, we get 18.5. When I divide by 0.5, you get 37. And so my upper index is going to be 37. If you started at 0 and use this expression here, there are some of you who are not, and that's fine. As I said, there's multiple ways of getting correct answers here. I see some people starting at 1 and ending at 38, and they have 1 plus 0.5 n quantity cubed. And that works too, because when I plug in 1, we get 1.5 cubed for the first term. If I plug in 38, 38 times a half, 0.5 is 19, 19 plus 1 is 20, and we end up with 20 cubed. As long as the expression I use and the indexing values I start and end with produce all the numbers in the sum, it is correct, whether it looks like the way Mr. Francis did it or not. If you have not looked at screen 17, please go do so. I will also open up screen 18. And then after this, we've got to move on to our last topic of the day, which will take us probably every bit of the remaining time left that we have. All right, so Monique on screen 17, your expression after your plus sign, because you have 0 in the numerator, it's always going to be 0. So you're not adding anything. You're not changing the term at all. Juan, your expression is not correct. Oriana, your expression is not correct. So a lot of you are you're ending your square root and your fraction, and then after you have your fraction with its square root in the denominator, you have a plus something. That's not going to work. Mathematically, that's just bad. I don't know how else to say it at the moment. You guys got to remember that all the rules of mathematics that you have ever learned still apply. So if you want to add fractions together, you need to have a common denominator. And if you have two separate terms, sorry, let me get to my notes screen. So a lot of you have this as your first term here, and then you want to add something here. This is going to have a common denominator with this one here if you want to add them together. And it's a mess to try to do it this way. I'm not even sure it's possible. I've never tried. But I know what a lot of you have is wrong from the start, so it's just not going to work. I won't say anything more just yet. Let me give people a chance to redeem themselves, try to fix it. Edson, I think yours looks pretty good. Alexis, do not put decimals in the indexing values. Remember, those have to be integers. So n cannot equal a decimal. The number on top of the sigma cannot be a decimal. They have to be integers. Get that mistake out of your system now, ladies and gentlemen. I think, let's see. Oh, Samuel. Okay, Samuel, I'm sorry. Yours looks a little funny. The delta is wrong on here. The amount it's grow each term that's changing is growing by is not 0.2 on screen 17. So that screws up your upper index also, your upper value for your index. Josh, I don't know why you're raising it to a power of -2. That's not mathematically the same thing. Ashley, that's not going to work, unfortunately. Sophia, that's not going to work either. And don't use X because you don't have X in your index. And it's just bad form to use X for that. No, Matt. All right, let me give some support on this one here. So the first term is 2 over root 1.2. The second term is 2 over root 1.8 plus 2 over root, what are we at, 0.6? So it's going to be 2.4. And eventually, I don't remember where I ended it, 14.4. So when I go to start building this with my sigma, that looks a little too crazy. What's always here? Well, we always have a 2 in the numerator. We always have a square root in the denominator. So I start by populating my argument with those things that are always there. Like I told you in the last couple of examples. Do we have 2 separate terms that are being added together? No, that's not a good way of thinking about it. Scratch that. What I'm saying has good intention. It's going to confuse you more. Think about each of these terms in isolation. It's just one term. There's no other sum. So all of you who are doing some sort of plus something over here are thinking about it wrong. Okay, so let's abandon that. Let's not think about it that way. It's the denominator here, the part that's under the square root, that's changing. So this is where my entire expression is going to go with, including if I start this at n, well, I don't know if I'm gonna I'll probably start it at 0. Wherever I decide to start it, that whole entire expression is gonna go here. What are we growing by? 0.6. So if you follow what I like to do, we'll start with our first term, 1.2. We'll add 0.6 n to that. And all of that goes underneath the square root symbol, 1.2 plus 0.6 times n. Now, I know we have to stop it somewhere, so I'm not finished yet. But what do I want to show you here? If I plug in 0 for n, I'm going to get 2 times root 1.2 plus 0.6 times 0. Then if I continue on to 1, 1.2 plus 0.6 times 1 plus 2 over, and if I put in 2, and then it's going to continue, but look at how this changes here. 0.6 times 0 is 0, plus 1.2 is root 1.2. That's exactly what I need for my first term. 2 over 1.2 plus 0.6 is going to be 1.8. So 2 over root 1.8 plus 2 over root 2.4, and then so forth. So this is going to work. I just got to figure out where to end it. And to figure out where to end it, I'm going to set 14.4 equal to our expression that I'm using. So that means 0.6n is going to be 14.4 minus 1.2, which is going to be 13.2. And when you divide by 0.6, we're going to get 22 out of it. Yeah, 22. And so this works. This is not the only thing that works. As I've shown you already, there are many different things that could work. But what most of you were writing with a sum outside of the square root, what you were writing was not going to work. I'm going to look at screen 18 and not wait too much, not wait too long here, because we got to get on to the last topic, which could take us a few minutes. We did those already. Okay. I'm going to open up 19 and 20, but we did those already just because I'm just opening up so I can get to 21 soon. Juan, on screen 18, why is your base 2? Not sun, Alessandro, sum with an M. Giovanni, I actually am not evaluating your whole entire expression as for its accuracy yet, although I think it looks pretty good, except I'd have to check your double check your upper index. It disagrees with some others. Doesn't mean they're right and you're wrong. I just don't know. But notice you don't have any parentheses around the exponential plus 5. So it's a little ambiguous. And although sometimes you'll see books write it the way you have it, it's preferable to put an open parenthesis before the 3 and a closed parenthesis after the 5. That way you know that that 5 is included as part of the summation criteria, the argument for the summation notation, as opposed to not being added after you do all of that sum. I hope you understand the difference about what I'm saying. So that we don't confuse our readers, it's better to put a set of parentheses there to know that sigma is acting on everything including the plus 5 and not just everything before that extra plus. All right, so as I'm starting to set up my structure for this one, we always have 3 raised to some power, and then we're going to be adding 5 to the result. So I'm going to put those things in there. And as I was mentioning a moment ago, it's good to have parentheses around the whole expression because there is a sum, that plus 5, that's also included in the summation. And if you don't have parentheses, your reader might be confused as whether it should be included or not. So let's not confuse our reader. 2.1 is where I like to start. We're adding 0.7, so 0.7 n. Then I'll start at n equals 0. And so my exponent here is going to be 2.1 plus 0.7 to the n. In Desmos, you probably have to put parentheses in the exponent to keep everything in there. Set that equal to 17.5. And we get 0.7 n equal to, if I subtract 2, I get 15.5. So 15.4 when I subtract 2.1. And so n is, that's another 22. I must have some default to my head where I keep mentally calculating these things in the same exact way and ending at the same index. Anyway, there's an answer that works for screen number 18. I don't have time to go through and check everybody's work right now, so I'm not going to do that. So some of you have a problem with not copying down things accurately for whatever reason. Maybe it's my sloppy writing, or maybe it's, I don't know. My point is copy better, pay better attention. We got to get to the last topic. We got to start it today. We'll work on it more tomorrow. What you're looking at here is a circle and a couple of squares. If you go back to ancient Greece, where, mathematicians like Archimedes and his contemporaries were trying to figure out how to find the area of a circle. Actually, I'm saying this in a way that's not, let me rephrase that. Back in ancient Greece, mathematicians were trying to figure out how to find the area of a circle with a formula. That's a formula we teach to what, 5th graders, 6th graders, 7th graders. I don't know exactly where it fits in that curriculum, but it's a relatively simple formula, but it's something that had to be invented a long time ago. And so around 2,500 years ago, you had mathematicians trying to figure out how to find the area of a circle, and they couldn't do it yet. It's at one point, okay? So what did they do? Well, they knew how to find the area of a square. And so what they did was they inscribed a square, that's the green one, inside the blue circle. By inscribing it, that means they put the vertices all on the circle itself. And they also circumscribed the circle with this square like the red one, meaning that all the sides are tangent to the circle. Why did they do this? Well, they did this because they could figure out that the area of, or they knew, it's obvious that the area of the circle was trapped between the area of those two squares. So if they found the area of the green square, they know it was smaller than the area of the circle. They found the area of the red square, they know it was bigger than the area of the circle. And so they had bounds, and upper and lower bounds. They said, okay, I know this is smaller, I know this is larger, and in between somewhere is the area of the circle. So although they couldn't find the area of the circle exactly, they were at least smart enough to put boundaries around it and say it's in there somewhere, whatever it is. Now, through some clever thought, they decided to increase the number of sides, and now they're using a couple of hexagons. And if you notice the difference between the last figure and this figure, there's a lot more blue area exposed here than there is in the new figure, meaning that there's a larger gap between the two squares than between the two hexagons. The inscribed hexagon has an area that's close, a little closer to the circumscribed hexagon, meaning the interval that they trapped the circle between is a little smaller. They continued. They added more sides to the polygon. Here's an octagon. Here's a decagon. Here's a dodecagon. Here's a 14-sided polygon. Notice that we're starting to get to a point where we can barely see the circle. Okay. Archimedes did this all the way out to a 96-sided polygon because he knew how to find the area of 96-sided polygons. That's all the way over here. If I drag this over, I know this number says 48. That's half the number of sides if you're paying close attention. You can't even tell that there's a circle there anymore. I mean, you could still see a little blue hint in between there, but the green region looks like a circle. It's not, it's a polygon. It's got all straight sides, but because the straight sides are so small, it looks circular. Why am I telling you all this bit of history here? Well, this idea of trying to find the area of a circle is foundational for our next topic. We want to be able to find the area bounded by a curve, not a circle. We know how to do that. Another curve, just some function. And I'll show you an example of that in just a moment. And we're going to do something very similar to what Archimedes and his contemporaries did, except we're not going to be using many different sided polygons. We're going to stick to some basics. We're going to stick to rectangles mostly. We'll use trapezoids also, just not today. And we're going to do something similar. We're going to find the area. We're going to use rectangles to approximate areas bounded by curves. Go to the Desmos activity and look at screen 21, please. On screen 21, we want to be able to find the area, or rather, let me rephrase that. We want to be able to approximate the area bounded by the curve. Just checking something real quick. Okay. Lost my controls here for a moment, ladies and gentlemen, but don't worry. I'll get them back. Okay, I'm sharing my Desmos screen with you. Now, what we could do to approximate this area is, and we're looking from 0 to 6, okay? I could draw a big rectangle around this like this, and that would be an approximation to the area bounded by a curve. Just not a very good one. Look at all this extra white space in here that the rectangle includes in its calculation. That's not part of the actual area that we're looking for. But it would work as an approximation, as an upper bound, if you will. If I was to get rid of that, maybe instead of using one big rectangle, maybe I would use a couple. Maybe I'd go from 0 to 6, 3 is right in the middle. Maybe I use, actually, that's not going to be very good. Whoops, I got to get rid of it here. Let's use 3 rectangles for a moment. Maybe I use this a rectangle that goes from 0 to 2, like this. And then a rectangle that goes from 4 to 2, that looks like this. And a rectangle that goes from 4 to 6, that looks like this. Now you might say that doesn't look very good. It's actually not as bad as you think, okay? This side over here gives me some extra area, but this rectangle over here misses all of this. And although those are not equal to each other, they kind of cancel each other out, at least in part, and that would give us actually a decent approximation. So what we need to do is we need to be able to find or put rectangles into our picture that are going to allow us to approximate the area by the curve. Now, if you notice in the instruction here, I said I want you to use left-hand endpoint rectangles, okay? And I want you to use 3 left-hand endpoint rectangles. So this is what I want you to do. What we're going to do first is we're going to calculate delta x. I'm writing it in here because I don't want to switch screens back and forth. You're going to calculate delta x by taking your values of your interval. We're going from 0 to 6, so use the right endpoint 6 minus the left endpoint 0. And I want you to divide that by the number of rectangles we're going to use. So it's the right endpoint minus the left endpoint, 6 minus 0, divided by the number of rectangles. So that means my delta x is going to be 2. That's how wide each rectangle is going to be. Let me repeat that. That's how wide each rectangle is going to be. My first rectangle is going to start over here at 0, and then it's got to be delta x units wide. So I got to get over here to 2. So this is my first rectangle, okay? We're going to call 0 x sub 0. We're going to call 2 x sub 1. My next rectangle is going to go, it has to be 2 units wide again. So I'm going to go from 2 to 4. I'm going to call that one x sub 2. My last rectangle is going to go from 4 to 6. It's got to be 2 units wide. I'm going to call that x sub 3. This is always going to be the pattern, ladies and gentlemen. We're going to do this every time. We'll get more practice tomorrow, but I have to introduce it today, okay? All right. Hopefully you're following along and drawing this on your screen also. I can't see because then I switch back and forth. So you should be drawing this on your screen because you can draw this. Now it says to use left-hand endpoint rectangles. What the heck does that mean? I'll show you. What you're going to do is you're going to go, I'm going to use a different color here so that we can distinguish what's going on. Let me use green. All right. So I got my first interval goes from x sub 0 to x sub 1. So I'm going to go over to my left-hand endpoint, because remember, we're using left-hand endpoint. So my first interval from x sub 0 to x sub 1, my left-hand endpoint is x sub 0. I'm going to draw a line straight up from the x-axis until I hit the function. Hit the curve, okay? I go right to there. And then what I'm going to do is I'm going to draw a horizontal line from that point over until I hit x sub 1. And then I'm going to complete the rectangle. That's my first rectangle I'm going to use. You guys know how to calculate the area of a rectangle, just base times height. We'll go calculate that stuff in a minute. Now, on my next subinterval, I'm going to do the same thing. My intervals from x sub 1 to x sub 2. What's my left-hand endpoint? X sub 1. So I'm going to start at x sub 1. I'm going to draw straight up until I hit the function. And then I'm going to draw a horizontal line from that point until I hit the function again. No, that's not true. I'm going to draw a horizontal line until I hit the value x sub 2, which happens to also hit the function. Draw that down like this. So I got my rectangle. Then I'm going to go to my next subinterval from x sub 2 to x sub 3. And I'm going to go to the left-hand endpoint, x sub 2. I'm going to trace it up, and it happens to be at the same height. That's okay. I'm going to draw this over to the right until I hit the next endpoint, which is at x sub 3. And then I'll complete my rectangle. Those are the 3 rectangles I'm going to use to approximate the area. Now, how wide is each rectangle? Each rectangle is 2 units wide. Remember, that's our delta x. How tall is each rectangle? Well, that's where I got to go do some calculations. The function value is where I get the height. So remember on this first subinterval over here, this is our height. How did I get that? By plugging x sub 0 into the function, because that's the y coordinate right here. So I'm going to plug in x sub 0. X sub 0 is 0. So I'm going to plug 0 into my function f. And what do I get when I plug in 0? I'm going to get 0 minus 3, negative 3. Negative 3 squared is 9. 9 times negative 1/2. That's negative 4.5. Yeah, negative 4.5. Negative 4.5 plus 6 is going to be 1.5. I'm kind of running out of space here, but this rectangle has an area of base 2 times height 1.5. So this has an area of 3 for this rectangle. How do I get the next height? Remember, I'm using left-hand endpoints. My left-hand endpoint right here is 2. So I'm going to plug 2 into the function and see what I get. When I plug 2 in, 2 minus 3 is negative 1. Negative 1 squared is 1. 1 times negative 1/2 is negative 1/2. 6 plus negative 1/2 is 5.5. Now, how do I find the area of the rectangle? It's 5.5 times 2. It's 5.5 times 2. That's 11. I would do the same thing again with the last rectangle. The last rectangle, I would plug 4 in. If I plug 4 in, you're going to find out that you get 5.5 again, and we're going to end up with 11 for that rectangle again. So what is my approximate area? 3 plus 11 plus 11. My area is approximately 25 for this one. Can I do it approximately? Oh, I guess it doesn't give me the approximately symbol. I would like the approximate symbol there. So the area is approximately 25 whatever. It might be feet, miles, meters, could be square units, depends on the context of the problem. But that's what I would put as my approximation. I went through that kind of quickly because, well, we only got like 3 minutes left or 4 minutes left. So I'm going to open up the next screen. You're supposed to do this again now on the next screen, but you're going to use right hand endpoints. I'm just going to run through it really quickly, ladies and gentlemen, so you guys can see it. I would start it all the same way. I would still calculate my delta x, That's still going to be, 6 minus 0 over 3. So my delta x is 2. My x sub 0 is always the left-hand endpoint. So I'm starting it at 0 because my left endpoint is 0. And then I keep adding delta x. So I add 2 to get 2 for x sub 1. I add 2 again to get 4 for x sub 2. I add 2 again to get 6 for x sub 3. And then I go draw my rectangles. Now I'm using right-hand endpoints. So from x sub 0 to x sub 1, I'm not going to do like I did before and go up at x equals 0. I'm going to go up at the right-hand endpoint, and I'm going to draw straight up from here all the way till I hit the function. And now I'm going to draw back from right to left until I hit x sub 0, which is 0. And there's my first rectangle. And then on my next subinterval from x sub 1 to x sub 2, I'm going to go to the right endpoint and draw straight up. Draw back until I get to x sub 1, which happens to be the same height. And I think we're going to get the same exact approximation here. Of course, that was my short-sightedness. Anyway, from x sub 2 to x sub 3, I'm going to go to the right-hand endpoint, draw up until I hit the function, and then draw across. And there we go. We have our 3 right-hand endpoint rectangles. To calculate the heights, the first height, I don't plug in 0 this time because 0 doesn't give me the height. 2 gives me the height. So I plug in 2. We saw that that was going to be 5.5. And so the area of this one is going to end up being 11. For the next interval, I'm going to plug in 4. I'm going to write the work over here because I'm out of space kind of over here. So I'm going to get 5.5 again, which gives me another 11. And then I'm going to plug in 6 this time. And if you plug in 6, you're going to find out, that you end up with 1.5 again. And that's all by coincidence, ladies and gentlemen. I didn't work it out ahead of time. I just made it up real quick last night. And funny, it works out to give me an approximation that's exactly the same as the other one, 25. Not what I intended. Well, I didn't have an intention because I mindlessly did it last night just really quickly. All right, ladies and gentlemen, it's 2 o'clock. You're now armed and dangerous. You have enough information to be able to do tonight's homework. If you have any questions, you can stick around. Otherwise, have a great rest of your day. And I will see you at 8 o'clock for the homework help hour tomorrow, or at 9 o'clock for the lecture, or maybe both. Have a great day, everyone. Bye, Angela. Have a good day. Bye, Edson. Have a good day. Yes, Juliana, on that question. Ariana, for the scale 2 came from, that's because we calculated delta x to be 2. And for calculating delta x, it's going to be the right endpoint, which is 6, minus the left endpoint, which is 0, divided by the number of rectangles. And so since we're using 3 rectangles, we divided by 3, and that worked out to give us 2. It won't always be nice numbers like that.
Sir, quick question. For the first box, why was it necessary to, why couldn't you just put like a little box, like 3 on the first one, instead of putting in like 11 and having more space outside?
We could have. The reason why we used that run is because the instructions told us to use right-hand endpoints. we went through this very, very quickly today. So let me preface what I'm about to say with that. I didn't have time to get into more options, okay? You certainly can, and if you're not told to do it a certain way, you certainly could have used it 3 for the first one instead of that, 3 for this one and 11 for the middle one as a different approximation. The reason why teachers give you a certain type of approximation to do is to make it easier on us when we go to grade everybody's work. If I told you just use any 3 rectangles that you wanted to approximate this area, then literally I could have everybody in the class give a different but true, correct, and valid approximation, which becomes a nightmare for me because then I'm going to have 32 different things to grade and I have to check every single one to be valid in its own right. But if I tell everyone to use right-hand endpoints, then I know when I do my calculation correctly and you do your calculation correctly, our answers should match. Makes it much easier for me to grade. Does that kind of make sense?
Yes, sir, definitely.
Okay. So whenever, I always tell my calculus students this, you literally can do any way, however you want to form your rectangles. You can use the maximum on the first interval, the minimum on the second interval, the midpoint on the third. You can use a random point on the fourth. And there's lots of different ways of doing it. The problem is it becomes a pain to grade and a pain to check the validity of it. And so for assessment purposes, to make sure that I know you understand how to do this, I'm going to tell you to do it this way. So that way, if you can get that answer, I know you understand the process. And then if you were on your own and doing it, for some other purpose, I have confidence that you know what you're doing and you'll be able to do it in your own way correctly on your own.
Sir, thank you. Have a nice day.
Thank you, Josh. You too. See you tomorrow.
Mr. Francis, I was wondering how you for the functions, how you got 5.5, 1.5 and stuff like that. I was wondering what the process of that was again.
I just plug the number into the function for x. So, our function is f of x equals -1/2 the quantity x minus 3 squared plus 6. So right here where it says f of 2, I just plug 2 in for x.
Oh, okay.
2 minus 3 squared is 1. 1 times -1/2 is still -1/2 plus 6 is 5.5.
Okay, thank you.
Anytime.
And also, Mr. Francis, for the test, I know I didn't do good, but I was